Let's see how machine learning can help us remove the jitter in this simulation. We'll be using a technique called PCA, Principal Component Analysis. Imagine we have a dataset of spheres with different widths and heights. These values can be plotted on a two-dimensional graph, creating a variation point cloud. The longest direction in our graph represents the greatest variation in the data. This is our main component, or the first principal component. Perpendicular to it, there's another direction of variation, but with less influence. But there's also variation in color. Well, we could add it as another dimension to our graph. It's a less significant feature that doesn't contribute much to representing our samples. By ignoring the least important components, we can reconstruct cleaner, simplified data, helping us remove unwanted noise. We provide the PCA node with geometry samples and let it determine which components are the most important. Let's prepare our geometry by adding a for each number loop. By setting the gather method to merge each iteration, we'll be replicating our mesh as many times as the number of iterations. Right now, there's nothing inside the loop, so the output will simply be the geometry from the current frame duplicated 10 times. However, to provide PCA with a proper set of samples, we need to include also a few frames before and after it. This will give PCA enough information to reconstruct our geometry as accurately as possible. To achieve this, we'll use an attribute called iValue, which acts as a counter and can be found in the forEachCount node, among other attributes. Let's reduce the number of iterations to 7 and see how the start value parameter works. On the first pass of the loop, the start value will be 1, and with each iteration, it will increment by 1. Then on the second pass, the counter increases by 1, so it will start at 2, then 3, 4, 5. Since we want to capture 3 additional frames before the current one, our start value should be set to -3. Let's add a timeshift node and set its expression to $f plus the iValue attribute from the forEachCount node. And voila, we now have 7 frames of our geometry, with the current frame being the central one. Drop down a principal component analysis. How many points are we using per sample? Each sample is a copy of our geometry, so we first need to check how many points the original geometry contains. 215,240 points. To make things easier, let's add a null node and name it something like ptCount. Back in the PCA node, we can use the endpoints vex function to read the point count from the null node we just created. However, our PCA node is showing a warning message. We are requesting more components than the geometry actually contains. So how many components do we have in total? Since we are using 7 samples, the total number of components is 7. To remove unwanted noise, we should aim to use as few components as possible while maintaining the fidelity of our geometry. What the PCA node is doing here is mapping the position of each point to generate a variation point cloud and identifying its first principal component.